All right, well, hello everyone, and welcome back. In this video, we're going to continue our discussion about pointers. And in particular, we're going to look at how pointers can be used to make dynamic variables and dynamic arrays. If you haven't already done so, please make sure that you have reviewed our previous two videos covering an introduction to pointers and those pointer practice problems. You'll definitely want to make sure you understand the basics before continuing on to this video. So here's the goals for today's video. First, we will briefly review some of the key points that we learned in our previous pointer videos. You'll definitely want to make sure you understand these key points before we move on. Next, we'll talk about the relationship between pointers and arrays. We'll find out that the name of an array is actually a pointer, which points to the very first element in our array. So we can actually manipulate arrays using pointers. We'll talk about some more details that are good to know. Finally, we will also briefly cover how to use pointers with functions, and we'll end by showing some examples of how pointers can be used to declare dynamic variables and dynamic arrays. Dynamic variables and dynamic arrays may seem a little bit strange and abstract, but it turns out that they're really powerful, and they're often used as a building block for more complex and powerful data structures like strings and vectors, and other things like linked lists that we'll learn about later on in the course. So let's first review just a little bit of what we learned in our previous videos. In our previous videos, we learned that a pointer is a variable that stores a memory address. We call pointers pointers because they point to a location in the memory. And so if you look inside a pointer variable, it's going to store a memory address or some specific location in the memory. In our previous videos, we also learned that there are some important rules to remember when working with pointers. You want to definitely make sure you understand these different rules and syntax details so that you can more easily understand and manipulate pointers. Let's briefly review these rules. Remember, we can use the reference operator ampersand in order to get the memory address of a variable. We also learned that to declare pointer variables, we need to use the asterisk in the declaration. We also learned that we cannot mix different data types with pointers. So if we declare an int type pointer can only hold an int-sized memory address. So you want to be careful to pay attention to the data type when declaring your pointers. Next, it's always a good practice to initialize your pointers. Remember, they do not initialize themselves. So once you declare a pointer, you want to make sure you remember to initialize it before actually using it or doing math with it. Typically, we initialize our pointers either to some other memory address using ampersand, or we can initialize our pointer to point at the null pointer, which is memory address 0. Also, you want to make sure you use the correct wording to describe pointers. And in our previous video, we gave some examples for that. We also learned some additional rules about pointers, which are really important. Remember, the asterisk is a very powerful tool when working with pointers. The asterisk allows us to do something called dereferencing. So if we use an asterisk and a pointer variable's name, This is going to allow us to access the value that we're pointing at. So asterisk PTR1, in this case with cout, this is going to return the value that PTR1 points at. Next point, when we use the assignment operator with a pointer, remember that is actually changing the memory address being stored inside our pointer variable. This will change where our pointer points. Notice that it changes the memory address stored in the pointer, but the memory that we're actually pointing at will not be changed. Finally, another very important rule is using the assignment operator and the asterisk together. Suppose I have my pointer, maybe it's that int pointer PTR. Suppose it's pointing at some variable. If I use asterisk PTR equals 10, that's actually going to say go where PTR points and change the data there to be 10. So using equal and asterisk together will directly change the value that that pointer is pointing at. And finally, where we left off last time, we started talking about the new operator. And we learned that the new operator can be used to create a new dynamic variable at that pointer's location. So we can create a new dynamic variable where our pointers are pointing. This is going to be a really important tool that we'll revisit more later on. Let's now briefly review the new operator just a little bit, and we'll return to it in more detail later on. You'll remember that the new operator will essentially allow us to create a brand new variable in the memory. What it does is it returns the memory address of a block of memory big enough to hold whatever variable you specified. So here if I have that int type pointer p1, and if I write p1 equals new int, the new operator is going to return an int-sized memory address. So p1 will now be pointing to some new memory address big enough to hold an int. So before we move on, let's go ahead and do one more practice question about pointers. If you'd like additional practice beyond this question, definitely check out our previous videos and our practice questions for extra practice. You'll want to make sure you understand how to solve questions like this, because you're definitely going to see similar questions in future assignments and exams. Let's try this review question. We are given that we have the memory shown in this picture. So we have P1 and P2, and they are pointers which point to int variables V1 and V2. And we're asked, what happens in the memory after the below code has run? So for questions like this, draw pictures. Drawing pictures will make it a lot easier to keep track of what is happening. So let's go ahead and draw on the existing picture we've been given, and we can go through this program line by line and keep track of what's happening. So in our first line, we have asterisk P1 equals 1. See if you can remember what these lines of code do. Remember, what's essentially happening here is we are going where P1 points and assign that data the value 1. So P1 currently is pointing at V1. So V1 is going to be changed from 10 to 1. Let's look at line 2 next. In line 2, we have asterisk P2 equals asterisk P1. Remember, the asterisk is going to tell us once again to go where P2 points, and we're going to make that data the same, make it the same value as the data P1 is pointing at. So notice here, asterisk P1, well, we look where P1 points. P1 is now pointing at 1. So asterisk P1 will return the value 1. So asterisk P2 equals 1. That's going to go where P2 points and set that value equal to 1. Let's now try line 3. In line 3, we have P2 equals P1. So that means we're taking our pointer P2. Since we're setting it equal to P1, remember, P1 is holding the memory address of V1 because P1 points at V1. P2 is holding the memory address of V2 because P2 is pointing at V2. So if I say to make P2 equal to P1, that means I'm changing the memory address stored in pointer P2. Pointer P2 is now going to hold the same thing that pointer P1 has. So now you can see that this line of code in line 3, we're making P2 point where pointer P1 is pointing. Because notice now pointer P2 and pointer P1 must be pointing at the same memory address. Now let's look at line 4. In line 4, we're saying asterisk P2 equals 999. What will happen here? Well, remember, if we use the asterisk in the name of the pointer, that means we are going to go where P2 points, and we're going to make that data equal to 999. P2 is currently pointing at our variable V1. So we're going to go to V1 and we're going to change the value to 999. Next is line 5. P2 equals new int. Remember what the new operator does? The new operator is going to return the memory address big enough to hold a new int type variable. And P1, or pointer P2, will now point to that new int variable. So notice, pointer P2 is no longer going to be pointing at P1's variable. Now pointer P2 is going to point at some new integer like this. Finally, in our last line, line 6, we have asterisk p2 equals 3. So we're going to go where p2 points, and we're going to assign that data the value 3. In this case, p2 is now pointing at our shiny new int. So in this case, that new int will be assigned the value 3. Notice in this case, nobody is pointing to our variable v2 anymore. So that variable v2 is no longer being pointed at by any of our pointers. So hopefully this was a helpful quick review for everyone. And by now you should be very comfortable following examples like this and visualizing what is happening. If you find that these pointers still feel a little bit uncomfortable or unfamiliar, please make sure you go back and review our extra practice problems and our examples in the prior videos. It's really important that you understand pointers well, because we're going to continue to use them in this course, and you'll definitely use them if you take more advanced courses like data structures. So feel free to reach out if you have any questions, and definitely make sure you can answer questions like this one. All right, with that, let's go ahead and move on to the relationship between arrays and pointers. Let's first start with a CODiSense question. Take a look at this code here. We're asked what will be the output from this code. So if we look at this code, what we're doing is we are declaring an array named numbers. So this is a little bit of a non-standard way of declaring an array, but it does work, where you can take an array and declare it with the curly braces. Here we are initializing this numbers array to contain 5 values. So normally I would recommend that you use a for loop to initialize your array. I do not recommend using this syntax, but sometimes programmers like to use syntax like this if they're just making a very small array or running a very quick test. So we have this array named numbers, and then look what we're doing here. We're trying to use a cout statement with asterisk numbers. What's going to happen here? Will this code compile? Or is it going to return a value? What does your CODiSense think? Take a moment and think about what this code will be returning, and then we'll discuss. All right, well, the key thing to remember with this CODiSense question is, what data does the name of an array hold? You might remember from our array lectures that the name of an array stores the memory address of the very first element, or element 0. So in this case, the name numbers stores the memory address where this number 10, or numbers element 0, is located. Well, wait a minute. A variable that stores a memory address is a pointer. So in this case, what's going to happen here is the name numbers is a pointer which actually points to numbers element 0. So if I say asterisk numbers, and numbers points to an int containing the number 10, we'll see that this code is actually going to return the value 10, because the name of an array stores the memory address of the 0th element. And in just a moment, we're going to see that the name of an array is actually a pointer, which points to that 0th element. So we can actually use the name of an array with our pointer syntax in order to manipulate the array's contents. In case you don't believe me, let's go ahead and run this program in CLion real quick, just to sanity check ourselves. Alright, so here we are in CLion, and we have our CodeSense question. So notice if I go ahead and run this code, you see that we do indeed get 10 as our output. We can even place a breakpoint on this line 7 and run the debugger, and we can verify. If we go and complete that expression, we see that numbers is indeed initialized to a 5-element array. And if we step through the program, we see that numbers, asterisk numbers, does indeed return the value 10. So the key takeaway here is to remember that when storing data in arrays, we've actually been using pointers. In C++, the name of an array is actually a pointer which points to the memory address of element 0. So because of this, we can actually treat array names like pointers, and we can use our pointer syntax with the name of an array in order to manipulate data inside. One thing to be careful of is the name of an array is a pointer that points to that array's element 0, but we're not allowed to change that pointer variable for an array. So that would basically assign a different memory address to element 0 of the array, which would be illegal. So you can treat the name of an array like a pointer, but you cannot actually change the memory address where element 0 is stored. Let's take a look at some examples to see how all this works. So suppose we have this array named vals. And here, just to keep things simple, we've declared vals to be an array containing just 3 elements, 4, 7, and 11. So you'll remember that the name vals is the name of the array, and vals is also a pointer which points to vals element 0. So since vals is the name of the array, it stores the memory address of vals element 0. So if I just write cout vals, I get the memory address where vals is stored. If I cout vals element 0, I would get the number 4. So when working with arrays and pointers, there are some important things we need to remember. Let's briefly review the things that we want to remember, and then we'll do some examples. Here are some of the key points that you'll want to remember when working with pointers, and specifically when working with pointers, arrays, and functions. As we mentioned, the name of an array is actually a pointer which points to index 0. or the very first element of our array. And so it turns out that just like how we would normally access an array element using vals element I, we could similarly access vals element I using asterisk vals plus I. We'll take a closer look at that in just a moment. Another thing to be careful of when working with arrays is out-of-range errors. No matter whether we use vals element I or asterisk vals plus I, we have to be careful not to go out of bounds. So we need to make sure we stay between element 0 and element n-1. In rule number 4, these rules specifically refer to using pointers with functions. We'll take a look at these in just a minute. We'll see that pointers and functions work very similar to arrays and functions. But with pointers, you need to have an asterisk next to the pointer declaration in both our declaration and definition. And then when calling, we use the pointer's memory address. So it's a lot like using arrays in functions, where with arrays you needed the square brackets in the declaration and definition and the name of the array in the call. We also know that while functions cannot return arrays, functions can return pointers. So we can declare a function to have a pointer return type. You just have to be careful to make sure that your function does not return a pointer to some variable that will be destroyed. If you return a pointer to a local variable that does not exist after the function ends, then you might run into problems like runtime errors. So you want to make sure, if you are working with pointers and trying to return a pointer with a function, you want to make sure that whatever you're pointing at will still exist when the function ends. That's one big advantage of using dynamic memory, which we'll talk about a little bit later. Finally, our last rule is a reminder that functions cannot return arrays. However, one important workaround is we can have a function return a pointer which points to a dynamic array. If we return a pointer that tells us where our array is, then that's basically just as good as returning the array itself, because we can then use that pointer to access our array later on. We'll talk more about dynamic arrays at the end of this video. Okay, so now that we've reviewed these things to remember, let's go ahead and go through some examples of each of these points. So, first thing to note here is that we can actually use the array name with pointer syntax. So, if we have our array named vals, I can write cout asterisk vals, and that's going to return, as we saw in our codesense question, it will return vals element 0, because vals always will point to the 0th element in that array. Notice there's a lot of interesting things we can do with pointers. Suppose I declare this pointer val pointer, which points where vals points. So essentially what we have here is we have our vals array containing 4, 7, and 11. Vals is the name of our array, which points at vals element 0. Here I've declared a second pointer named valptr, which I'm also making point. Valptr also points at the same location as vals. But look what I can do. If I write cout valptr square brackets 1, this will actually advance valptr to the next element in my array, and it's going to return the value there. So I can actually use a pointer that's pointing to my 0th element in the array. I can treat this pointer like an array with the square brackets, and I can have it move around inside my array. Let's look at another short example of this. In this example code shown here, we are declaring an array and we declare a pointer. So we have this pointer named P and we have an array named A. And notice we have some outputs here, so we're showing the memory address where A is stored, and we use a for loop to show that initially our A is initialized to numbers 0 through 9. And then we initially have our pointer point to null. But then you'll see what we can do is if we set our pointer P to point at A, we see that if we use cout P and our square brackets, we can actually output the same data as if we were using our array name A. Let's take a closer look at this program using CLion. Okay, so here we are in CLion, and notice we have our int type pointer named P, and we have our array named A, and we have this variable named index that we're using to step through our array. Notice if I put a breakpoint, say on line 23, and I run the debugger, I can verify that initially my array is completely initialized to numbers 0 through 9. So we see our pointer P is currently pointing to null, and our array A, if I look inside, I'm initialized to 0 through 9. And if I continue stepping through my program, notice in this next step, I set my pointer P to point where element 0 of A is located. So if I set pointer P equal to A's memory address, this pointer P is going to change. So now we can see pointer P is pointing at A's memory address. So if I go ahead and look through there, I can see that if I output P to the screen, I can get the same data as in my array. I see my pointer is now pointing at A's memory address, and we see that P outputs the contents of my array A. You can imagine if you're trying to design some very complex data structures that use arrays, being able to use pointers to search through your array can be really powerful. So key takeaway here, if we set a pointer to point at the same memory address where the name of our array points, we can treat that pointer like an array, and we can access all the data inside of our array. So we mentioned that there were some interesting tricks and tools that we could use to actually search through an array using pointers. Here's some examples. Suppose I have that vals array again. So if I declare this vals array with 3 elements, 4, 7, 11, and if I declare that int type pointer valptr and make it point to vals element 0, look what I can do. If I write valptr++, I can advance my pointer valptr to the next element. So now this is pointing at vals element 1. Before I was pointing at vals element 0. Or if I decide that I want to instead move to the previous element, then I can say val ptr minus minus, and notice this is actually going to shift my val ptr one element earlier in my array. There's also some funny little tricks we can do when accessing data. Notice I have an asterisk and I have parentheses here. If I say asterisk val ptr plus 2, that means I go where val ptr points and I increment by two items in that array, and then I can return the value stored at that index. So here, asterisk parentheses val ptr plus 2, that will return the number 11 to the screen. Be careful though, you need these parentheses. If I just say asterisk val ptr plus 2 without parentheses, that would just give me 4 plus 2, or 6. So notice the parentheses do matter, because parentheses force us to do val ptr plus 2. That shifts the whole pointer by 2 before determining the value stored. Let's look at a couple more examples. Once again, let's assume that we have this vals array and val ptr as our pointer. If I want to permanently shift my val ptr pointer, notice what I can do is I can say my pointer val ptr equals val ptr plus 2, or I can write val ptr plus equals 2. This will allow us to advance 2 elements farther down the array. Or if I want to go I elements, I could do plus equals I. Here's another really interesting one. Suppose I want to know how many elements are between vals and val ptr. If I write cout val ptr minus val, that will output the number of elements between those two. So here, vals is at element 0, val ptr is at vals element 2, so val ptr minus vals will be 2, because these two pointers are 2 elements apart. And finally, suppose I wanted to bring my val ptr pointer back to the beginning of my array. I could just write val ptr equals vals, and that would make the 2 pointers point back at the same memory address. Finally, last couple examples here. Notice that we can also use that val ptr pointer to manipulate data in our array and access data inside. For example, val ptr element 1 would return the value 7. Or I could say val ptr element 2 equals 20. I could assign that second element the value 20. I could also write asterisk val ptr plus 2 equals 20 to do the same thing. A lot of this syntax might seem a little bit confusing or redundant. So you might be wondering, why do we have this extra syntax? Why do we have these extra capabilities? For ordinary arrays like this one, we don't necessarily need to use pointers to access our data, because we can directly access the data through the name of the array, vals. But we'll see later when using dynamic arrays, we will have to access our data through pointers. So it's important to know these alternative ways of manipulating data in our arrays. Let's briefly summarize. So the key things to remember about accessing array data with pointers are shown here. We can see that if we have this array named vals, notice we can rewrite vals square brackets I, that is equivalent to asterisk vals plus I. And now we have different methods we can use to access data in an array. The old-fashioned way is just to use the name of the array and square brackets. But in a dynamic array, our array will not have an official name. It will only be accessed by a pointer. So being able to access an array's contents using a pointer becomes very important. So you should know that all four of these methods shown are valid ways to access data in an array like this one. Make sure you remember that no matter which of these four methods you use, you will not be able to check whether or not you're within range of the vals array. So be careful to avoid out-of-range errors, and make sure you stay within the bounds of the array. You don't want to accidentally step outside the size of your array because you might end up messing up someone else's memory. All right, so let's continue on with a few more notes about pointers and functions, and then we'll finish up with dynamic arrays. One more thing that's important to bring up about pointers is comparing pointers. Please make sure you remember that comparing the memory address where a pointer points is not the same as comparing the contents that the pointers are actually pointing at. So one way to think about this is if we think about our pointer, if we have like PTR1 and PTR2, and if these pointers are pointing at some variables named V1 and V2, remember a pointer points at the memory address that is being stored inside the pointer itself. So the actual variable stored inside PTR1 will be the memory address of the variable V1 where pointer 1 is pointing. Similarly, if PTR2 points at V2, then PTR2 must be holding the memory address of V2. So here, if PTR1 double equals PTR2, this will compare the memory addresses stored inside each pointer. And notice the difference where if I have the asterisk, if asterisk PTR1 double equals asterisk PTR2, then that will compare the contents that PTR1 and PTR2 are pointing at. So make sure you pay attention to the asterisk, and if you need, draw a picture to help you notice the difference. All right, last couple points from our list earlier. We're using pointers and functions. So remember that pointers can be used by C++ functions, and they work a lot like arrays and reference variables. Pointers can be helpful if we want to be able to change stuff within our function. Remember, if we use the asterisk with the name of a pointer, that will allow us to access and manipulate data that we're pointing at. So if we want to declare a function that takes a pointer as an argument, notice that we need to have an asterisk on the pointer itself in the declaration. And we also need to have an asterisk in the definition. And then, of course, if we want to actually return the value that the pointer is pointing at, we still need to use dereferencing. But notice if we want to actually use the pointer in a function call, we have to use the memory address that we want to plug in for that pointer value. So very important to remember, you need the asterisk in the declaration and definition of your function. If you want to access the value, then of course you have to use dereferencing with the asterisk. And you have to plug in a memory address when you're calling the function, because remember, pointers store memory addresses. So you have to be able to plug in a memory address in for your argument pointer. So here's an example of how pointers can be used as arguments of functions. Here we have two functions, one named getNumber and one named doubleValue. Notice both of these functions take int-type pointers as their arguments. And so notice in order to accept that pointer as an argument, I need to have an asterisk for the pointer declaration, both in the function declarations and in my function definitions. Also, if I want to actually get the input inside my function body, notice I have to use asterisk in order to manipulate the data where that pointer points. For example, in getNumber, I'm using cin asterisk input in order to take a number from the monitor and from the keyboard and store it in my pointer input. And then finally, notice that when I call getNumber and I call doubleValue, notice that I plug in the memory address of a variable. And that memory address will be plugged in to my pointer. So it's important to remember to use the ampersand to get the memory address of whatever variable you are substituting in for that function call. Make sure you remember these three rules whenever you're working with pointers as function arguments. You'll see that if we run this program will allow us to actually double a number back inside our main function, similar to pass by reference. And that's because we are actually sending the memory address of number into our functions. So our pointers are able to directly change the value stored at that memory address by using pointers and the dereferencing. Let's give this program a quick run in CLion. So here's our program in CLion, and we can see we've got our functions declared, and notice we have our getNumber function that will take some input from the screen and send it and store it into our input pointer. And then we have that doubleValue function that will actually use the dereferencing operator in order to double the value of the data stored at that memory address. So if I go ahead and run this program, we can see what happens. First, we declare that variable number. We call the getNumber function. When we go to getNumber, I'm going to be asked to enter an integer number. Say I give it the number 5. I'm told that I entered 5. We go back into main, we call doubleValue, and then doubleValue will use our pointer in order to double the number stored. Then we look back in main, and our value number has been doubled to 10. So pointers can be really powerful. They can allow us to directly manipulate memory at the locations specified at the pointer's memory address that it holds. So you also want to be careful then to make sure you don't accidentally change memory that's unintended. So you want to be careful to pay attention to what your pointers are doing in your programs. So let's briefly cover returning pointers from functions. We don't do this super often in this course, but towards the end of the semester we'll do a little bit of pointers and functions. And if you take future courses in data structures, you'll probably be doing this a lot. Notice we can declare a function to have a pointer as its return type. So a function may return a pointer, but you want to make sure that you are not returning a pointer to a local variable in your function. Remember, local variables will be destroyed when the function ends. So if you try to return a pointer to a variable that doesn't exist, you're probably going to create some bugs. Definitely some runtime errors or other problems. So make sure that if you are returning a pointer, make sure that you are returning a pointer to data that was passed in, maybe as an argument from main, or you can return a pointer to dynamically allocated memory. We'll talk more about dynamic memory in a moment, but remember that is memory when variables declared using the new operator. Let's do a quick review question before we move on. See if you can identify the false statement about pointers and functions. Take a moment, see if you can find it, and then we'll discuss. Let's go ahead and find the true statements first. We know that choice C is true. Functions can definitely return pointers. We also know choice A is true. We need to put an asterisk in the declaration and definition when using pointers with our functions. Choice B is also true. When calling, we need to pass in a memory address. You have to plug in that memory address so that our pointer can use it in its function. Choice D is the false statement. So be careful here, because if you return a pointer to a function's local variable, local variables will be destroyed when the function ends. So just because you have a pointer pointing to that local variable, that's not going to save your local variable. Any variables local to a function, that's basically any variable declared within a function, those variables will no longer exist when a function ends. So you want to make sure that if you return a pointer, make sure it will point to something that does not get destroyed after your function ends. Alright, with that, let's go ahead and talk now about dynamic variables. Because one way to make sure that your variables will not be destroyed when your function ends is to use a dynamic variable. And we'll learn that dynamic variables are really powerful building blocks that we can use to create more powerful types of data structures. So why do we bother with these things called dynamic variables? We call dynamic variables dynamic because they are created and destroyed while the program is running. You might be thinking, well, why would we want to do that? And for simple programs like what we've done up to this point, you don't necessarily need dynamic variables. But suppose you are Google or Amazon or a big tech company, and you're managing data from millions of users. You're not going to know ahead of time how much data or memory your customers are going to need. So, depending on what your customers are doing, you need the flexibility to be able to create more data on demand or allocate more memory on demand. Also, sometimes we don't want our variables to be automatically deleted when the function ends. We want to be able to control when our variables are created and destroyed. And also, sometimes we just want flexibility to be able to add or remove data while our program's running, and we don't have to go back and change some global constants and recompile our program. We want flexibility. And dynamic variables allow us to do all of these things. Let's review a few key points about dynamic variables. These are key points that you'll definitely want to remember. First, dynamic variables are created using pointers and the new operator. Again, we call them dynamic because they're created and destroyed while the program is running. Up to this point in the class, we have actually been using a different kind of variable called ordinary variables. So any variable we declare inside main, or any variable we declare in other functions, these are generally ordinary variables, sometimes called automatic variables. These variables are going to be automatically created when our program starts, and these variables are automatically deleted when the program or the function using them has ended. So there's nothing wrong with ordinary variables. They're still good. But sometimes we need more flexibility. And that's where dynamic variables come in. Here's another important difference about dynamic variables. Dynamic variables are stored in a different part of memory known as the heap. Some textbooks call the heap memory the free store memory. Ordinary variables are stored in a different part of memory known as the stack memory. And so, one other advantage of using dynamic variables is you can use a different part of your memory when working with them, so it can buy you a little more flexibility if you have a limited amount of stack memory. Heap memory is not infinite either. At the end of the day, you're limited by how much RAM your computer has, but it can provide us more flexibility. Here's another interesting thing about dynamic variables. Dynamic variables must be deleted manually. So dynamic variables will only be deleted when the program ends or when we use the delete operator. So when a function ends, our dynamic variables are still going to exist. They keep existing until we're no longer running our program or until we delete those variables. But with power comes responsibility. Because if we want to have these variables that must be deleted manually, we do want to make sure we remember to delete them when we're finished. Because we don't want to get into a situation where we run out of memory. So a good practice is to use the delete operator when we're finished with our dynamic variables. That will free up our heap memory. And that will also help us avoid creating what's called a dangling pointer. Alright, so let's now cover a few more points about dynamic variables. First, one thing to note is that if we do not have enough heap memory available, our program will automatically terminate. This is part of C++ standard, so any compiler, any IDE will give an error and terminate if you don't have enough memory. Also, as we mentioned, even on small programs, it's a good practice to delete your dynamic variables when you're done using them. So we call this recycling our memory, and we use our delete operator to delete our dynamic variables when we're finished. That way, we don't accidentally forget about those dynamic variables and clog up our memory. For us in our small programs, it might not seem like a big deal, But you can imagine if you have millions and millions of variables and you forget to delete some of them, you can very quickly cause problems. So get in the habit of using the delete operator to delete your dynamic variables when you're finished. It's actually really easy to use the delete operator. All you have to do is take the word delete and then the name of the pointer, which points to that dynamic memory. So in this case, suppose my pointer p was pointing at some new int that contains some value. If I say delete p, all that's going to do is that's going to delete my new int. And now my pointer p is just going to be pointing at nothing. It's basically uninitialized again. So the delete operator will just delete whatever dynamic variable our pointer is pointing at. But you want to be careful. You want to make sure you don't accidentally delete something important, because if you use this delete operator, you can create what's called a dangling pointer. Dangling pointers are pointers that do not point to anything. And you can imagine that if you have memory you forgot to delete and pointers that don't point to anything, you can create major problems in your programs because you can create runtime errors and all sorts of issues with that uninitialized memory. So dynamic variables are nice, but an especially important application of dynamic variables is dynamic arrays. Let's talk a little bit more about dynamic arrays. Remember, so far, when we've talked about arrays, we've always had to specify the size of our array when writing our programs. But here's the problem. Typically, that means we have to know in advance how big we want our array to be. So typically we estimate the largest possible size to be safe. We don't want our array to be too low or too small, otherwise we might run out of space. But if we make our array really, really big, we're wasting memory. So dynamic arrays actually help us avoid some of these issues. With a dynamic array, we can actually use a variable to specify the size of our array. This way, we can get an array exactly the right size every time. So let's take a closer look at how dynamic arrays work, and we'll end with a couple examples. So dynamic arrays are arrays that are created using the new operator. And the really nice thing about dynamic arrays is we can specify the exact size we want using a variable while our program is running. We don't have to know ahead of time how big our array must be. And the nice thing is, once we've initialized our dynamic arrays, they behave the same as regular arrays. We just use the name of the pointer, which points to that array. So instead of using the name of our ordinary array, we access our dynamic array using the name of its pointer. You might think all this extra stuff sounds kind of silly. Why do we bother learning about dynamic arrays? And the reason why is because we've actually been using these already. Vectors use dynamic arrays, and also strings use dynamic arrays too. You know how when you declare a string type variable, you don't have to say how many characters your string contains? C++ just makes you a string with the size that you need. So vectors, strings, a lot of the more advanced C++ tools, they actually use dynamic arrays. But all of the functions, all of the code, it's hidden away in those include headers that we keep at the beginning of our program. And again, one more thing to note about dynamic arrays is that, once again, they live in the heap memory, not in the stack memory. And so this can give you a little more wiggle room because it's an extra set of memory that we can use when we're working with our arrays. Let's now discuss how to declare both one-dimensional and two-dimensional dynamic arrays. It's actually pretty straightforward. To make a 1D dynamic array, we just need to follow these 4 easy steps. For a 1D dynamic array, we just need to declare a pointer variable, and this will be used to create and access our dynamic array. And this pointer must point to the same data type as the type we want our array to be. So in this case, I'm just going to go ahead and declare this pointer called D. So I have this pointer D. Currently, it's uninitialized. In the next step, I can use the new operator to create that dynamic array with the desired number of elements. So here, this array size, this can also be a variable. We do not have to pre-specify array size ahead of time. And in this case, notice what's happening is we're taking our pointer D and we're making it point to a whole set of doubles. These are dynamic. This is our dynamic array, and it will be of array size elements. And notice our pointer D points to our very first element. Once we've declared this array, we can manipulate it just like a regular array. All we need to do is use the name of the pointer and our square brackets. So I could write a for loop like this and say D element I equals I. If I do that, that would initialize each element in my array to be that element's position. Finally, when we're done with this dynamic array and we want to just delete that whole thing, notice what we do is we use the delete operator with some square braces next to it. We need to include these square braces in order to delete all the elements in that array. Otherwise, we'll only delete the first element. So if I use delete with square braces D, that will delete everything that's left and leave me with an uninitialized pointer D. Let's go ahead and take a quick look at an example of creating a 1D dynamic array. So this example shows one way of making a dynamic array, and we have this global constant array size But we can show that for dynamic arrays, we can also use a variable to specify the array size. Remember, with ordinary arrays, we had to specify the size as a constant. So notice this program does kind of similar to what we demonstrated. We declare that pointer D. We make D point to that new dynamic array. And now we've initialized this dynamic array so that its values, we just number the elements. Another really helpful tool to visualize dynamic arrays is to use this website called pythontutor.com. If I go to C++, I can put my sample code from earlier in Python Tutor. And I can push this button for visualize execution. And by doing this, notice what I can do. I can actually go through and run this code line by clicking Next. I can see in my main function that I've declared my array size to be some value. I've declared this pointer D, and look what happens. When I say D equals new double array size, you can see that I have now created this dynamic array on the heap. Meanwhile, my variables declared in main, since they are not dynamic variables, they are in the stack memory. Now I can go through and keep running, and you can see that my output now shows I have just created my dynamic array, and I can use this for loop to go through, and I can visualize and watch as I update each item in my dynamic array using this for loop. So if I go next, you can see that I can go through and update each element I of my dynamic array to hold the counting variable I. So element 0 is going to be updated to be the number 0. And then I'm going to output that number to the screen. So you see it's displaying 0 on our output. If I repeat this for loop, you can see that if I go through, for loop keeps running and I'm able to initialize all the values in that dynamic array. And so finally, we've created all of our dynamic array. And notice now that we have finished stepping through all the values, we're about to delete that dynamic array. And look what happens when I run the delete operator on line 23. Notice now I see a little icon here because we have just deleted our dynamic array, and now our pointer is pointing to uninitialized memory. And so notice now we're getting a warning from Python Tutor because we might want to change D to now point somewhere else to avoid potential errors. Definitely consider using this Python Tutor website to help you visualize dynamic arrays. It can also be a helpful tool for ordinary arrays as well. Now let's suppose that we, instead of using a constant for our array size, we ask our user to tell us how big we want our array to be. So I'm just going to quickly change this program. I'm going to use refactor. I can use refactor to rename this value, and I'm just going to rename this value as size. And instead of making it a constant, I'm going to make it a variable. And I can ask my user, And now, notice we're not getting any errors, but we can go ahead and we'll declare that dynamic array to be however big size is. Unfortunately, Python Tutor doesn't do as well with inputs and outputs, so we'll just run this code in CLion. So here, let's say we want our dynamic array to contain 20 elements. So notice if we do that, we created our dynamic array with 20 things, no problem. This is really powerful, and this is what strings use, what vectors use, and what you'll use in more advanced data structures courses in order to create different types of data that will be the exact correct size. Let's do a quick review question before we move on. See if you can identify the false statement. Let's first identify the statements which are true. Well, we definitely need the new operator when declaring a dynamic array. We also can use our dynamic array just like a regular array once it's declared. And we can also delete our dynamic array using the delete operator. Just remember, in this case, we want to use the square braces as well. The false statement is choice B. Our pointer does need to point to the same data type as our dynamic array's data type. Because remember, pointers can only store memory addresses of the same type as that pointer. So if we want a dynamic array of doubles, we need to declare a pointer of double type. Here's one other thing you should know about when working with dynamic arrays. This is not going to be covered on exams, but I do think it's good for you to know about this thing called typedef. Some programmers like to use a typedef as a shortcut when defining different kinds of variables. For example, if I don't want to write int star when declaring a pointer of int type, I can use a typedef. In this case, I called it int ptr. And so now whenever I write the word int ptr, that is the same as writing int star. So some programmers like to use typedefs because they can save themselves some asterisks and other code. It's not absolutely required. It's more of a style choice. But in some programs and some textbooks, you'll see that the programmers and textbooks choose to use typedefs when working with dynamic arrays. I personally do not use typedefs because I don't think it really helps. It kind of just creates more work in this case. I do not expect you to use typedefs. But if you see a typedef in example code or in our textbook, now you know what it is. Here's an example of how a typedef might be used. So in this case, they declared a typedef. Instead of double star, we are now going to write double ptr whenever we want to declare a pointer. So it really doesn't save a lot of work here because we could have just written double star d, but instead we made a typedef, so now we can write double pointer d. Otherwise, the approach for declaring the dynamic array is the same as before. All right, finally, let's go ahead and wrap up with multidimensional dynamic arrays. Multidimensional dynamic arrays are very similar to one-dimensional dynamic arrays. However, the process for declaring multidimensional dynamic arrays is a little bit more tricky. So you want to make sure that you understand how it works. Remember, multidimensional dynamic arrays are basically just arrays of 1D dynamic arrays. So if we want to declare a 2D dynamic array of int type values, the first thing we actually need to do is to declare a 1D dynamic array of pointers of type int. So notice what we do. We actually write int star star PTR. Remember, star is the syntax for making a pointer. So int star star will create a pointer to an int star type. So we're making a pointer type pointer. And then we can use this array of pointers to point to more arrays. And what we can do here then is, now that we have this 1D array of pointers, then we can use a for loop to make each pointer in our 1D array of pointers. We make each of those pointers point to a 1D dynamic array of ints. So notice essentially what we're doing here is we are stacking multiple 1D dynamic arrays together. And when we stack multiple 1D dynamic arrays, we create a 2D grid or 2D dynamic array. So here you see, if we have this for loop, we can actually create a 2D dynamic array with 4 rows and 3 columns. Notice that we use the number of columns to specify the size of our int array, and then we use the number of rows to specify the size of our 1D dynamic arrays. That way we end up with rows and columns in our 1D dynamic array. So declaring the 2D dynamic array is a little bit more work, because you have to declare these two separate things, the array of pointers and then the arrays of individual ints. But once you've declared this 2D dynamic array, then you can access elements using the same syntax as ordinary arrays. So here, notice I can write ptr element 1, 2 equals 99, and that will allow me to go to, in column 0, 1, 2, notice I can change ptr element 1, 2 to be 99. So once you've declared that multidimensional dynamic array, you can use for loops and our square braces and our indices, just like you know for regular arrays. Let's look at one quick example of dynamic arrays before we end. Remember, we mentioned that you do not have to use a constant to specify the size of a dynamic array. In this example, we're actually asking the user to tell us how big we want our array to be while the program is running. And once we know how many rows and columns we want, then we declare that 2D dynamic array. So we use a pointer that points to an array of pointers, and then each of those pointers we make to point at another 1D set. So we basically build up our dynamic array one column at a time. And then finally, we give our user the opportunity to enter the data into our array, and based on the user's input. And then we output our dynamic array to the screen. Finally, just for fun, I've also included the code you would use to delete that dynamic array. Since the program is about to end, technically you do not have to delete the array here, but notice you have to use the delete operator twice. Once to delete individual rows, and again to delete the array of pointers that was used to create that dynamic array. All right, so here we are in our sample program. We're asking our user for how many rows and columns, and then creating that dynamic array. So first we need to tell our program how many rows and columns we want. How about 2 rows and 3 columns? So now we're asked to write 2 rows of 3 integers each. So you keep it simple, we'll do 1, 2, 3, 4, 5, 6. And there we go. We've got a 2 by 3 two-dimensional array. Let's go ahead and wrap up here for today. You should now be more comfortable working with pointers and using the pointer syntax and rules that we've covered. You should also be more familiar with the relationship between pointers and arrays. Make sure you understand the basics about how to manipulate arrays using pointers. These tools become especially important when working with dynamic arrays. Make sure you remember the rules when using functions that take pointers as arguments. Remember to include asterisks next to the pointers in your declaration and definition. And remember, when calling a function that takes a pointer as an argument, you need to plug in a memory address for that pointer to hold. Finally, make sure you've gone through our examples of dynamic variables and dynamic arrays. Consider using that Python tutor website to help you visualize what's happening. Drawing pictures is also very, very helpful. Feel free to reach out if you have any other questions on pointers and dynamic arrays. Remember, these may seem a little bit intimidating at first, but once you get comfortable using pointers and dynamic arrays, they can be incredibly powerful tools. So definitely take the time you need to understand them, and feel free to reach out if you have any questions. Thanks everyone for joining the fun, and we'll see you in the next video.